So we're going to go back to graphone again. Let me go over the theorem, right? Um, so we have constructed a piecewise kernel out of the matrix of the connection weights, right? Out of the Wij. So you construct this piecewise constant kernel. And then we have this miracle theorem that says that, you know, up to reshuffling things a little bit, then we have compactness. So we can extract a subsequence, and we are going to have some sort of strong convergence. So maybe let's start with this, right? Let's discuss a little bit from a technical point of view, what is this topology of operator? Now, I'm going to repeat the definition of the norm of an operator, which I'm sure you all remember, but this is useful, right? So if I have a W bar and I'm taking the norm and I'm going to denote it like that, right, as operator, this is, of course, the supremum of all function in L infinity. Of the norm of the thing as a kernel, so W bar side zeta f zeta d zeta, right? So you use the W bar as a kernel. This gives you a new function, which is a function of psi. You take its norm in L1, and you divide by the norm of f in L infinity. Okay. So no surprise here. Right? You just want f to be non-zero for this. Okay. So the one thing that we can realize just based on this formula is this is it's weaker than LP norms, but it's still a reasonably strong norm. So it's weaker than LP norms because, of course, if I can bound this by the L1 norm of W bar. Right? So, for example, the integral of W bar sine zeta f zeta d zeta, right? If I just pull out the L infinity norm of f, this is f in L infinity times the integral of W bar sine zeta d zeta. So, of course, if you insert this here, the L1 norm just means integrating and psi because everything is positive here. So W bar in L infinity to L1 is less or equal than the L1 norm of W bar. So weaker than any LP norm. But it's still a strong norm, so that in particular, if I have some weak convergence of W bar, then I do not have, in general, the weak convergence in the operator norm. So W bar and converges weakly wherever you want to take it. For example, to W bar for the weak star topology of L infinity because they are uniformly bounded in L infinity. So let's say we have that, right? This I can always get up to an extraction, of course. Then in general, the integral of Wn bar of psi zeta for any f, right? Does not converge strongly in L1. Right? It's very, very easy to come up with counterexample. I can just take W bar n of psi zeta, which is a product. Okay. So omega of psi, omega of zeta. Let's even take it symmetric, right? And then obviously omega n of psi doesn't converge strongly, so that's it. So it's a strong norm, okay, but it's weaker than LP norms. Now, in the context of graphon, there's often a mention of something which is called the cut distance, which I'm not going to define here, which is essentially equivalent to this norm. So if you hear cut distance, there's another way of defining those things, which is equivalent, that I'm not going to be using. Okay, fair enough. Now, can we understand a little bit why something like that is true? And the answer is yes. So again, I'm not going to give a complete proof here for the sake of time. I'm just going to sketch a few ideas. So sketch of why this is true. And let me recall a very famous result, which is sometimes called the polar decomposition of a function. So given a certain function, right, which is integrable, of whatever space you want, omega, right? I can write the symmetric decreasing rearrangement. Right? And then so this is the object. This is a function of one variable now that has exactly the same level sets as f. It has the same level sets. It means it takes the same values and the size of the level sets are the same, and it's decreasing. And then there exists a measure preserving phi, right, such that you can represent f like this. So it's almost everywhere. And this is very, very well known. What this tells me, right, is that up to a measure preserving rearrangement, I can change f into a function that is decreasing, and therefore if f was in L infinity BV. So in particular, if I now have a sequence, uniformly bounded in L infinity, and the symmetric rearrangement, right? So again, that I can get up to a measure-preserving map is uniformly bounded in BVs, therefore it's compact in L1. So if you give me one sequence, one function, I can compactify it by a measure-preserving map. And this is very simple. What actually happens is this is a game that you can play with any sequence of sequences. And you have the following theorem, which is a bit technical to prove. So now I'm going to consider f and k, right? N is an n, and k is an n as well, okay? So I have a sequences of sequence. But they are all uniformly bounded in infinity. And as a matter of fact, I only need that, for each k, so soup in n of f k L infinity to be finite for all k. Then you can compactify them, can compactify all the sequences at the same time. So there exists phi n not phi n k. Phi n does not depend on k, right? Such that f n k composed with phi n is compact in n for all k. This is very fun, fun fact from analysis. It's a formulation that I like especially. It's more or less equivalent to something that is called the regularity lemma for graphons. But as I've written, it's really a formulation that we are using in a paper with Poyato and Soler. And I'm not going to give a proof. It's a bit technical. You have to hierarchically cut the space and then do rearrangement one step at a time, trying to mix everything all together. You can even have an explicit regularity result here. So I can tell you what is the modulus of continuity in L1. It's a little bit of a crazy thing, so I'm not going to write it down, but it can be completely explicit. And this is the sort of thing that is going on, okay? So with this theorem, you can prove the other one, for example. Right, so I'm going to consider a certain family GK in L infinity, right, which is dense in the unit ball of L infinity, but for the L1 norm. Because of course, L infinity is not separable, so you need it to be dense for the L1 norm, right? And now, so I have the W bar n, and now I'm going to consider the following f and k of psi, which is the integral of W bar n of psi zeta gk of zeta dz. And I'm going to compactify those. All right, so I'm going to get 1 phi n such that fn k psi is compact in L1. Phi n of psi, of course, all right? And then it's relatively simple to check that because the GK are dense and because the F and K are all compact, again, for every fixed K, then this will give you the compactness of W bar n. As operator, again, in L infinity 12. All right. So I'm not going to say much more about the proof of graphon. Again, this is really just a sketch, but it gives you a bit of an idea of what's going on here. Now, however, so we have this very nice result, okay? And again, it tells us that at least there's a scaling of the Wij, such that we have convergence in the right norm, right, for graphon theory. Now, the question is, can we then use this to get to the field limit? All right. So the strategy is going to be relatively simple. So we had built this piecewise constant kernel out of a Wij, so no problem. I am now going to build a piecewise constant empirical measure to go with it. I'm now going to define an empirical measure, an extended empirical measure. In the following way, I am going to sum. Take, of course, the Dirac maps. But instead of, just stopping here, I'm going to put the Dirac mass at the right location in psi. So what happens in right? If this is psi and this is mu n bar, is again, I'm cutting in slices. And in the slice that corresponds to I minus 1 over n, I over n, right? So that slice here, I'm going to put delta of xi. And of course, if I integrate this mu n bar in dxi, I find the classical empirical measure that we had used on Tuesday. Now, and the remarkable fact that happens within this simplified framework is I actually have a relatively nice and simple equation on mu bar. And in the absence of diffusion for simple pairwise interaction, it's well known that the classical empirical measure for identical particle solves actually the limiting Vlasov equation. And the same phenomenon happens here. This is a simple exercise in distribution. So in the sense of distribution, I have the following equation where the interaction term, the nonlinear term, now is going to use W bar n. And so for identical particle, the game was to pass to the limit in the Vlasov equation for measure solutions that are measured, that are measures. And here it's the same thing, right? I have to pass to the limit into this equation. But of course, now this is not the limiting equation, strictly speaking, because here I have W bar n, not the limiting kernel, right? So I need to pass to the limit into this equation, and that requires two things, right? Extracting convergence subsequence for mu bar n, that's easy enough. Mu bar n, it's L infinity in psi, and it's measuring x, so fair enough. We'll use the compactness of the unit ball of a dual, right? We'll get some weak star convergence, and we need to pass to the limit into W bar n. Right, so I'm going to have mu n bar, which converges weak star to some mu bar. And again, I have W bar n, which converges strongly, but for the operator norm to W. And the question now is this working, right? Can I pass to the limit into this equation? Of course, what you can see immediately is if we had a strong convergence in some LP norm, right, of W bar n, then this would be immediate. Right, and this is immediate because, of course, W bar n of psi zeta mu bar n of t dy zeta, right? Remember that mu bar n is bounded measure L infinity, right? Measure in y, L infinity in zeta. This converges strongly in L1, so in psi and zeta, So this will converge, all good. And in particular, if I integrate, again, a kernel that is at least continuous in y and x and then t, zeta, then this converges strongly to the limits, right? Because strong in zeta against weak in zeta, that works. But we do not have a convergence in LP. So here, there's the need to be a little bit more careful. A little bit more careful. And I'm going to skip over the painful technical part. That's not super hard, but I just don't have half an hour to do it, completely rigorously. I'm just going to point out that if we can separate the y and the psi in this, right, then this is obvious. So this needs to be extended. And I'm just going to make a very obvious remark that gives you an idea. Right, so if I had an Fn of psi only, right, that converges weak star in L infinity to F of psi, weak star L infinity, then by definition, right, of the compactness of W bar n of psi zeta, Fn zeta t zeta, converges strongly in L1 of psi to the integral of W psi zeta F zeta t zeta. And in particular, if I, again, try to freeze the y and x variable in this nonlinear term, right? And just look at something that now if Fn psi, the integral of Wn bar of psi zeta, Fn zeta, t zeta, then that converges weak star to F psi, integral W psi zeta, F zeta, t zeta, because again, product of weak star convergence against strong convergence in L1. And weak star in L infinity, strong in L1, that works. Okay. So basically, you have to take this very obvious remark and you have to extend it in a manner that makes it compatible with having an extra variable x and y. As long as k is smooth, this is not a big deal, and this can be done at the cost of several more technical steps. Right? And then that's it. We derive the same Vlasov equation as in 3.2, right? On the weak star limit of the extended empirical measure. X star. Now, this took a bit of time to figure out. There's a whole series of paper by Medvedev and Chiba Medvedev in particular that started about 10 years ago and that finally got to this sort of formulation using graphon theory that I'm going to refer to here. Chiba Medvedev. Some of them are done only for the Kuramoto model, but it's very easy to extend them to just any Lipschitz interaction using the same techniques. All right, so this is it for graphon. Again, this is just a very, very brief overview. As before, maybe now is a good time to stop and see if you have questions, and then we'll get into the final part.
Any question? Pierre, maybe you go ahead.
Yeah, of course. All right. So, why is there more to be said here? Well, there's more to be said here because to do all of that, we had to take a very precise scale. And that scaling was, we needed to assume that all of those were of order 1 over n. Now, first, a quick disclaimer. There are some ways to extend graphons outside of that scale. This is important because the first problem, right, with this sort of scaling is it basically prevents us from having sparse graphs of interactions. Now, you might not be fully connected, but you have to be close to be fully connected. Otherwise, if you have a sparse interactions, right, that is, if most of the Wij are 0 and all of them are of order 1 over n, well, you know, then the total weight of a connection acting on any individual neuron is going to be super small. And so then, yes, you do have a mean field limit. The mean field limit is nothing moves because the interactions have disappeared. So it's not very interesting. Okay. So if you want to have sparse interactions, right? So if the agents are not going to interact with almost everybody, but they are really going to interact only with a small subset, then you need to have some very large weights. Otherwise, it's completely boring. And we have plenty of applications where we know that the connection weights should be sparse. If I'm going back actually to my example with biological neurons, right? In the human brain, we have a bit less than 100 billion neurons. Let's put this down. Right, something like 86 billions. But the average number of synaptic connection per neuron is between 5 and 10,000. So clearly you are sparse. And very obviously something happens. So very, very obviously for this particular application, you cannot take Wij, which is a folder one array. All right. So as I said, you can extend some extensions of graphon theory to sparse setting. Now, I'm not going to go too much into the details of the literature here, so I'm just going to give a very, very brief overview. First of all, you have some sparse random graphs. Right, so now the connections are not deterministic, they are random with very precise scaling, and you need a lot of structure on the graph. So this has been done for the so-called Erdos Shreni, for example. And if you don't know what it is, don't worry, it's one particular well-known type of random graph. You have also various extensions of graphons themselves. This requires a renormalization. So in particular, what is key for those sparse random graph is the weights might be large, but they still all have to be of the same order. So that way you can renormalize all of them and get to something that is order one. So yeah, you have also other extensions, things like graphops and so on and so forth. But everything that we have that is graphon based right now requires some notion of a structure that is predetermined and that is given to you. And I am not saying that this is that we'll never be able to deal with it like that. Actually, I'm fairly convinced that there should be some sort of extension of graphon with some sort of extension of the operator norm that we just discussed, so that we can still do what I showed you, still pass to the limit into the Vlasov equation and all of this. The issue is I have no idea what it is as of today. So instead, I'm going to have to do something nasty, which try to bypass the Vlasov equation. And again, this is the big obstacle here, right? It's not so much finding any crazy extension of graphons that is going to write for a sparse graph. It's finding an extended distance, right? So that this analysis here that we've just done can still be carried out. And that's what I don't know how to do. So I'm going to sketch instead a new approach that we put together for the first paper with Poyato and Soler that I already mentioned, and then the second paper with my students Tatongzu. All right. And the approach relies on, the key is a new notion of something that we called observables. So there's a little bit of a loaded language here whenever you mention observables, right? But fundamentally, the idea is very straightforward, right? As I mentioned before, when looking at the Vlasov equation, we do not care about the f or the mu bar of tx psi, because we can't really see the variable psi, right? It's not something that is given to us in general. It's something that is implicit. So the first observable, right, we've already seen it. At the limits, this is just the integral of mu bar tx psi d psi. And at the level of the dynamics, right, well, I can play the same game. So I can take the mu bar n of tx psi d psi. Now, that's a nice observable only in one circumstances, however, when you don't have random initial condition, okay? Because otherwise, this is a random measure. This is not something that you can actually easily physically measure either. So in general, you need to put an expectation. And if you go back to the definition, right, so this was the classical empirical measure. So this is the expectation of a classical empirical measure. So this is just that. Fi tx, where Fi is the law at time t of agent number I. And it's not the law, it's the probability density, but you'll forgive me the slight abuse of notation, I hope. And this is a very natural object, right? So now I have agents. They are all, or particles. They are all different. So their individual law might all be different. But I'm still interested in the one particle distribution, and the only way to give a definition of this one particle distribution that makes sense and that actually respects the only symmetry we have in the system is just to average all the particle distribution. And this is the first observable. This is the first thing that we want to see. This is something that does not depend on how you parameterize in psi. But there are others. Why there are others? Well, very, very simple. So now let me call this F capital N 1, right? Just one particle of T and X. I can write an equation. And whenever I have a many particle system and I'm writing an equation on what is an extension of a one particle distribution, I'm going to hit the two particle distribution. So no surprise here, I have a linear equation which involves a two particle distribution. Or the extended two particle distribution, right? So this is something I can calculate. I have an explicit formula for F1n. I have an explicit equation for each of the individual law, right? Just take the ethos formula applied to the many particle system. So this I can calculate. And what do I find? What is the term that shows up here? It's the following second observable. And I'm going to, and now I need to know the joint law of two particles. And so Fijn is the law of the pair xi xj. And this gives me the second observable. And I can repeat the process. So Fn2 is the second observable. I can write an equation on Fn2, and then I'll find some third observables. There's only one third observable. But then I write an equation on the third observable, and I have several fourth observables that show up. And that's because things are not symmetric anymore. And so you see that the weights start entering into those observables, into the definition, and they keep on entering, and they enter in different ways. And so this leads to a family of observables that is indexed by trees. And we have a general formula that is going to sound horribly painful to you, but I'm still going to write it down. So the observables corresponding to a certain tree on capital T has the following expression. This is 1/n. The sum of all choices of certain numbers of particles, the number is equal to the number of vertices on the tree. So I1, IT, I'm going to denote absolute value of T, the number of vertices on T. And then I have a product of a certain number of weights. And it's very simple. I'm going to take all the edges of the tree, and I'm going to make the product of the weights corresponding to all edges, right? So to each vertex, I assign one particle. And then once you have an edge, I know the pair of particles. And then I need the marginal. So E of t is what? E of t is all the edges t. And then I have the marginal, and the marginal that corresponds to I1, IT, right? So 15, X1, XT, so Fn, I1, IT. This is the law of X, I1, X, IT. And what you see from the way I have proceeded is this is the minimum family that represents the dynamics. And it bypasses the question of how to parameterize, right? So how am I going to choose psi? Bypasses the whole thing. And now there's something really fun that happens. We have a closed hierarchy on the observables. And so the big question now becomes, can I get uniqueness? And in general, getting uniqueness in BBGKY hierarchy, and this is, of course, a lot worse, because again, indexed by tree, instead of having a very simple countable family, well, still countable, but the way it's indexed is much more complex. So it's worse. But there is a very, very nice remark that we made at the time, which is if you have non-vanishing diffusion, then you can get uniqueness. Now, I didn't put diffusion in my system, so you might tell me, well, you might have a bit of an issue here. Not really. Because if K is Lipschitz, I can actually add artificial diffusion to the dynamics, and I know how to control the difference. And if you do all of this, and again, here, the technical details are really hopeful, so, but I'm not going to spend 2 hours on that, given that I have 5 minutes left. And I didn't plan on going into there because, right, we would have to spend the whole mini course basically working out the technical details about how do we get uniqueness, how do we write the hierarchy, how do we connect it to the limit. There's a lot of technical things that need to be handled very, very carefully here. But if you do all of this, you still find the same Lazarev equation at the limit. On the one particle distribution, right? So what I called F1. For some W psi zeta, which is a crazy thing. Because now it's not in L infinity anymore. It's a weird object, which is some sort of function that is an L infinity of a first variable measure of a second variable, and you can swap. So L infinity of the second variable measure of the first variable. And let me just, before someone yell at me, let me just say that for me, this is just the topological dual of L1. continuous function. All right. So you get a Vlasov equation, yes, but you get it for a kernel that is potentially a very, very crazy object, much more complicated than before. You cannot go through the limit directly through the Vlasov equation, at least I don't know how to do it. So you need to bypass completely taking limit in Vlasov by going to those crazy hierarchies. But in the end, everything works. And you get back to the ideal setting that we had described in section 3. Right. So that is a very brief overview of the most difficult case, again, on purpose. I just want to mention that this idea that diffusion can help you get uniqueness in a BBGKY hierarchy was obviously in the air because while we were finishing this on the non-exchangeable system, Dan Lacker actually used that to get new convergence rate for identical particles using the relative entropy. And then we use it later, still for identical particles, to derive a Vlasov-Poisson-Fokker-Planck, at least in dimension 2. So it's a very natural, very powerful tool using diffusion to get uniqueness on infinite hierarchies. Right, we'll stop here, and if you have any question.
Yeah.
Thanks for your lecture. And in the end, you still derive a similar Vlasov equation with the kernel W.
We derive the exact same form of the Vlasov equation that people in neural field, for example, for biological neurons, we are deriving already in the late 60s.
Yeah, and I'm also wondering, in your setting, does you still assume at the particle level that the weight is a function of psi?
No.
But you can.
The only assumption here, I should have written this. My generalized mean field scaling, right? So the sum of the weights in a row is bounded, right? Is of order 1. The sum of a weight in a column is of order 1. And each individual weight goes to 0. But that's it. I am not assuming any structure. You don't give me anything. Right? The Wij can be any crazy matrix. The only thing I'm asking is the sum of the columns, the sum of a row are of order 1, okay? And you don't have any big individual entry. They don't have to be of order 1 over n. You're not giving me any psi I, any psi j, any w of psi I, psi j, anything like that. And we still find them.
I see. Thank you. But I have a follow-up question. Is do we know how does this kernel depends on this weight? Do we know more like concrete information?
Not at all. Not at all. And it's not only that, right? Remember the discussion already in section 3, in section 4, that I can always change the kernel. Because I can always play with measure-preserving maps, right? And as a matter of fact, if you're a little bit careful, the map doesn't even have to be measure-preserving. So you can really do crazy things here. So I can completely transform the limiting equation, transform F1, transform the kernel, get something that looks like a completely different equation. But they are actually the same, right? They solve the same thing. They have the same dynamics. They produce the same observables.
Yeah, yes, thank you. And I have another detailed question. Could you elaborate a little more about how the FN2 what is the tree for FN2 in your example?
Oh yeah, the FN2 is a very, very simple tree. It's just the tree with one root and one leaf, right? So let's call that T2, right? That's it.
I see.
And of course, if you look at trees with three vertices, right, they are all homeomorphic as well. Because it's 1, 2, 3 or 1, 2, 3, but then if you take a different root, they are the same. So that's why the third observables, they all come down to the same function as well. It's just switch the order of the variables. So you really need to go to at least the fourth observables to really start seeing the tree come into place, because the trees with 4 vertices now, they are not all homeomorphic.
I see. Thank you.
Yeah, Pierre-Emmanuel. So when you derive the observable, so this Fi, so F1, F2 to small f, right? So F1 to Fn.
Yeah.
So it's not the law for the ice particle, right? So I read your paper.
So again, the system is, the particles are not identical, right?
Yeah.
So if you're looking at the laws of the pair of particles, they could all be different.
Yeah.
If you take another pair, it could be a different law. Right? So my F, if I just take Fn ij, right? Again, the simple tree with just 2.
Yeah.
Okay.
But, I want to say, so from your yeah, go ahead.
This is really for an identical system. This would be just the second marginal.
Okay. Yeah.
Right? Because for an identical system, everyone would be the same. The law of xi, xj would just be the law of x1, x2. But here, that's not true anymore, right? So I need to keep track of all the laws of every individual pairs. Right? And when I go to the bigger observables, those Fn I1, I T, right, number of vertices in the tree, they can, again, be all different.
Yeah.
Right? Because here, yeah, if you change one of the particle, the law might change.
Yeah, but so like in your paper, like GSP paper or GPS paper, so so you define the observable according to the, so those Fi things are solution for coupled PD, right?
Yes. So that was the earlier paper with Poyato and Soler, right? Where we first did propagation of independence, and so then we could get to a system where the particles were independent, but you still had coupled equation on the law of each individual particle. But what we realized in the second paper with Datong, that actually deals with biological neurons, which is so integrated fire system, which is much harder even than that, because you don't have an exact hierarchy, because you have jumps, so it's more complicated. But what we realized is that we could define the observables directly using the law. We didn't need to have independence given to us.
Yeah, nice. Thank you. Is there any more question? Okay, maybe I ask a last one. Okay, so in general speaking, like for mean field limit for non-exchangeable particle system, do you think is there some like important but not well investigated problems?
I think for a very long time people thought that if you knew how to do the cases with identical particle, then you would know how to do non-identical. And it's not always wrong. Okay, I showed some example where this is actually completely accurate, but it's not always true either. And so yes, I think we missed some important applications and some important examples where having non-identical particles really changes things. And again, think of how important it is when you're studying function in dimension n, right? And there's a whole list of functional analysis tools that have been built about. But they've been built for a symmetric function in dimension n. And now if you take away the symmetry, right, it's a very natural question to say what remains of those tools? What is still true? What is not true anymore?
Yeah, sure. Yeah, for instance, like previously we used the monotonicity of relative entropy, right? So if even the reference mirror is RID, right? So if the first argument of the mirror is not symmetric, we don't have the control, right? We don't have the HN controls HK something. Yeah.
Yes.
Yeah.
Yes. For example, right?
Yeah.
With entropy, it's going to be.
Yeah. Okay. Yeah. Maybe.
It's a good question, right?
Yeah.
And again, it's not that it completely disappears. I can still look at the entropy, the relative entropy for non-symmetric functions.
Yeah, Pierre-Emmanuel, there's one more question from the audience.
Thank you for the great talk. I had one question in the last part for graphene. So the trick to add a diffusion term only works for the kernel when it's Lipschitz. But what if the kernel has worse regularity? If it's like locally Lipschitz, is there a way to get around with that?
No, not that I know.
Okay.
I have no idea how to treat kernels with singularity here.
But what if you have some weakly dependent particles for the finite particles, can you use some benefit from that structure?
Sometimes this is a very specific, example-specific answer. So sometimes yes, sometimes no. Again, in the weakly non-exchangeable case, you keep quite a bit of a structure. You just lose some symmetries. So sometimes things are still going to work the same, and sometimes they are not. I'm sorry, I can't give a general answer here. It's really case dependent.
Okay, thank you.
Okay, let's thank Pierre-Emmanuel again. Yeah.
Thank you. Bye.